This will be a tutorial on the Bellman-Ford algorithm for single source shortest paths, which may have negative weight edges. So it will include a description of how the algorithm works, an image description, pseudocode, and a description of the running time. So a quick introduction to how it works. We'll find the shortest path from a single source vertex to all vertices connected to the source in a directed weighted graph. Bellman-Ford is going to work on a graph with negative weight edges. Unlike Dijkstra's, which we saw before, Bellman-Ford will work with negative weight edges. We have to insist that the graph will be directed because undirected negative edges imply a negative cycle. You can go either way across the edge, and if it's negative, that implies a negative cycle, and we can't have that. So to start, we're going to let the distance of the start vertex equal 0. The distance of the start vertex from the start vertex, so that makes sense. And then we're going to let the distance from the start vertex to every other vertex equal positive infinity by default, as opposed to null or anything else. It's going to be positive infinity by default. So where n is the number of vertices, we're going to iterate over all edges in the graph n minus 1 times, performing the relaxation procedure, which is where we test for a shorter path. When we finished iterating n minus 1 times, if there are no possible relaxation operations left, then we found all shortest paths. When we finished iterating n minus 1 times, if there still are potential relaxation operations remaining, then the graph contains a negative weight cycle. So that was just a quick introduction. We'll do the real learning here. This is our graph. Yellow lines are edges, these are edge weights, these are vertices, the red circles, and they're just named A, B, C, D. This is where we're documenting our progress using Bellman-Ford, and this is where we're documenting our progress using Dijkstra's, just to compare the two and show how Dijkstra's doesn't do very well when we have a negative weight edge. So anyway, we'll do Bellman-Ford because that's what we're here for. So we have A, B, C, D. And unlike Dijkstra's, which uses the greedy choice method, we're just going to use alphabetical order to choose which vertex to look at. So we start at A, and the distance from A to A is 0. So A to B, A is connected to B, and the distance is 1. A to C, A does reach C up here. If you look above this little arc is A to C. The distance is 0. And A does reach D, and the distance is 99. So now where in Dijkstra's we would have looked at like C, right? Because this would have been marked the shortest path and closed off for the rest of the thing, the algorithm. Then we would have looked at C because it was the smallest besides that. Instead, with Bellman-Ford, we're just going to look at B. We're just going in alphabetical order because we're looking at everything anyways. We're not closing off A here, even though we know intuitively that the distance from the start vertex to itself is going to be smaller than any other way we could get to the start vertex. We know this is the smallest path. We're still going to keep going. Anyway, so we're at B. So B doesn't reach A because this is a directed graph, right? It only reaches C. Doesn't reach B, so that's still the same. It reaches C with a distance of 2 here and here. 1, 1 is 2. It's not better than the 0. It doesn't beat the 0. And we're not reaching D. So let's look at C. So C to A. C doesn't reach anything, doesn't have any outgoing edges, so everything's going to be the same. D. Okay, now we're looking at D. Well, D goes to B. So D to itself, it doesn't help anything. But D to B is minus 300. So this path from ADB, which is 99, and then minus 300, this is our negative weight edge, that's going to be negative 201. That's a hell of a lot better than 1. It's a shorter path. So we're going to replace 1 with negative 201. And then C, like D is not reaching C, and it's not, and it kind of, I guess you say it reaches itself, but it doesn't change anything. So 0 and 99 are still there. That was our first iteration because we've gone over A, B, C, and D and compare them to A, B, C, and D. So if you remember, we're going to be doing the number of vertices minus 1 iterations. So we got to do 3 iterations, right? So here's iteration number 2. So we'll start back at A again, same thing, just alphabetical order. A to itself is still 0. A to B, A reaches B with 1. The shortest path though is still negative 201. A still reaches C, 0 is still the shortest path from A to C. A still reaches D, 99 is the shortest. And here we get a little change. So we're on B. B reaches C. And remember what B is. Like the distance from A to B right now is minus 201. So like we keep that in mind as we go. So from B to A, B doesn't reach A because it's, remember, directed. It only reaches C. B to B, whatever, minus 201. Now B to C is going to be, well, B is minus 201. We add 1. Now we're at minus 200. That's a faster path, or shorter path rather, than 0. So it's minus 200. D, B doesn't reach D. It's still 99. And then we look at C. Doesn't have any outgoing edges. Everything will stay the same. D, we've already sort of accounted for this minus 300 here. So, you know, okay, everything stays the same. And we're meant to do a third iteration here, but our third iteration, as you might be able to predict, is just going to have the same values: 0, minus 201, minus 200, and 99. So the algorithm that we will check in our pseudocode here will do the third iteration, but we don't have to do it here. We know it's going to be the same. Let's look at Dijkstra's real quick and see what would have happened. This is why we can't have negative weight edges and analyze that graph using Dijkstra's. So Dijkstra's is going to do this. It's going to go A to A is 0, A to B is 1, A to C is 0, A to D is 99. That's all good. And then, okay, we're looking at A, so it's the greedy method, this local optimum. We call it the global optimum because that's how we're using our greedy method. We don't have to look at A for the rest of the time. Now, we're going to look at C because C is the next lowest. So, C doesn't have any outgoing edges, so everything's still the same. 1, C is 0, D is 99. So that's going to be our local optimum. And so Dijkstra's would consider that to be the global optimum too. But like Dijkstra's would not look at C for the rest of the time. It would be like we saw in Dijkstra's video, just empty after this. But we know from using Bellman-Ford that it actually goes down to negative 200. So that's why we don't use graphs. We don't use Dijkstra's on graphs with negative edges because we might have a negative edge later on in the path. The way that Dijkstra's uses the greedy method, it's assuming that we're never getting any shorter. The further we go, we're only getting longer. And so we can count on these local optimizations to be global optimizations too. But when you make the path shorter with a minus 300 edge, you can't do that anymore. So that's why we have to keep going over and over it like this. That's why we use Bellman-Ford, and that's why we can't use Dijkstra's with negative edges. Here's the pseudocode. I'll try to finish this quickly for you guys. So it accepts a graph G of vertex V. This is how we start. We set the distance from the start to itself to 0. We set the distance of every other vertex to positive infinity. We're going to just have a simple for loop from, we're going to iterate number of vertices minus 1 times. For each directed edge, UZ outgoing from U. This is the relaxation procedure. So if the distance to the vertex so far, the distance to U so far, plus the distance from U to V, or from U to Z, is less than the distance that Z already has. So we have this new path coming from U. If that's shorter than the path that we already had to Z, then we'll make the path to Z that new path that we just found. And then after we're done iterating, like we said this many times, in our case it was 3 times. We only showed 2, but explained that it was 3. If there's no edges left with potential relaxation operations, like ours was, we're just printing out the same thing each time. We're not making any progress. There's no potential for progress making relaxation operations. Then we'll just return the distance labels of each vertex. That's what we chose to do. Else, if we're done this iteration 3 times and we're still able to make progress with relaxation operations, then G contains a negative weight cycle that we got trapped in. So this is Bellman-Ford can be used to detect negative weight cycles. The running time's pretty easy. The while loop iterates n minus 1 times, where n is the number of vertices. On each iteration of the while loop, for each edge, m, in the graph, we do constant work. Therefore, the running time is O, N, M. Vertices times edges, because again, we loop number of vertices times, and inside the while loop, we have a for loop that's doing number of edges times, so we multiply them. There's just constant work inside. So that's Bellman-Ford. Check out Dijkstra's algorithm video on this channel because it's related.